Hello dear Abaqus users! In this workshop we plan to teach you sequential thermomechanical analysis of simple cube one direction LPBF 3D printing using the trajectory based method by AM Modeler plugin. Laser powder bed fusion or LPBF is one of the common additive manufacturing technologies. During laser powder bed fusion, the recoater first deposits a thin layer of material powder. Then the laser beam scans along a predefined path acting as a heat source to melt and bind the powdered material into a solid structure. So we said sequential, didn't we? Long story short, to do a 3D printing simulation with the LPBF method, we use a plugin in the Abaqus. In this plugin, we create two models. We do a heat analysis on the first one. You can see the heat analysis of the first two layers here. Then we do a structural analysis in the second model and apply the results of the heat analysis to this one and print the model. You can see the printing of the first two layers with a scale factor of 10 here. In the end, the model will look like this. Don't worry, we'll explain more later. Wasn't that much of a short story, was it? Now let's see our inputs for this simulation. The build part is a cube with dimensions of 1 mm by 1 mm by 1 mm. And the build table is considered as a cube with dimensions of 1 mm by 1 mm by 0.25 mm. You can see the assembled state of the build part and the build table. The required properties in this analysis are the following: conductivity, density, expansion coefficient, latent heat, elastic and plastic properties, and specific heat. The build part starts from here. And this is the build table. The construction direction is global z-axis. The build part is supposed to be made in 10 layers, so the thickness of each layer will be 0.1 mm. From this table, you can see the expansion coefficient, which is a function of temperature. Also in this table, the conductivity coefficient is presented as a function of temperature. Latent heat is defined as the heat or energy that is absorbed or released during a phase change of a substance. It could be either from a gas to a liquid or liquid to a solid and vice versa. You can see the value of the solidus temperature and liquidus temperature. Also, the density of the powder is like this. And specific heat and its dependency on temperature are listed in this table. Here we present Young's modulus and Poisson's ratio as a function of temperature. Also, the plastic property of the material is like this. Look at this picture again. There is a roller that adds the powder to the powder bed. It does this job in a path with a specified speed. Also, there is a laser that scans the powder in a path to create a component with a specified speed. You can see the speed of the roller and the laser here. The speed of the roller and the laser are according to the 3D printing machine we're going to use. Just remember, these values are just our assumptions and they're not according to a real problem. The big question is how we are supposed to define the path and the speed of the roller and laser in the Abaqus. We do this task using two datasheets, which we would call them event series, one for roller and one for laser. The laser event series includes the time, location of the laser beam, and the power of the laser. The laser moves continuously with a specified speed. The speed is specified by these data we apply in the software. The first column of these data represents the time. The next three columns are for location of the laser beam and the last one for the power of the laser. For example, at a time of 0.4 seconds, the coordinates of the laser are 0, -0.4 and 0.1. Next, in the time of 0.42 seconds, its coordinates are 0, 0.6, 0.1. The difference is only in the y component, and with the speed equation, you can calculate the speed of the laser beam. You can see that from the data that the speed is constant, because that's how we entered our data. Don't worry, you'll understand better when we explain it in the software. And the material event series is for the roller movement and how the powder is added. The first four columns of these data represent time and the location of the roller. The speed of the roller is calculated the same as the laser. You can see that from the data that the roller speed is constant. The last column is about when the roller is off or on, which we explain later. These data will be at your disposal as a text file along with the videos. Now let's see the boundary conditions in the heat transfer model. The initial temperature for the build table is 353 Kelvin. And the initial temperature for the build part equals to the initial temperature of the powder, which is 313 Kelvin. In the structural model, all degrees of freedom at the bottom of the build table are fixed. Before we go any further, let's walk you through what we are trying to do here. In the first step, we'll define two thermal and structural models required to start the AM Modeler plugin. First, a thermal analysis is performed. Then the results, which are a nodal temperature field, will be applied to the structural model as a predefined field. After that, the structural analysis will be performed. Sequential means the thermal analysis is done first and then structural analysis. Both models have geometry, mesh, material properties, boundary conditions, and of course a series of predefined fields.